Reinforcement learning in drone racing has outperformed human champions on known racing tracks. However, these agents fail on unseen track configurations. We proposed an adaptive environment shaping framework by leveraging a secondary RL policy to design environments that strike a balance between being challenging and achievable, allowing the agent to adapt and improve progressively. Every n iterations, the environment policy takes the racing policy evaluations and current environment data as input, adjusting gate layouts for each parallel environment. After the racing policy trains on the new layouts, it generates a relative ranking reward, and SAC is used to update the environment policy. The racing policy utilizes the information about drone and gate states from these simulation environments to learn time-optimal drone racing strategies through an MLP. We demonstrate the changes in gate layout during the training process by choosing 3 time steps: 200 iterations, 1,000 iterations, and 15,000 iterations. As the racing policy is trained, the environment gradually generates more challenging gate layouts. Here are the videos of our real-world results. We tested our method on 6 unseen tracks. Among these 6 tracks, 3 are 2-dimensional, and 3 are 3-dimensional. All of these tracks are outside the training distribution and have never been seen in the simulation. Notably, all experiments are conducted using the same racing policy. From the videos, we can see that the racing policy trained by our method can fly smoothly on different tracks. A single drone racing policy trained with our framework can successfully race on various tracks with different levels of complexity in the real world, achieving a 100% success rate, whereas the state-of-the-art curriculum learning approach often fails to fly.